Let me go over some selected homework problems from 4.2a. So this is from page 267 to 268. Here are all the homework problems, but I'm only going to be picking out either ones I think are good for you to see or ones I'm going to be going over in class. So number 9, use sigma notation to write the sum. So we're trying to represent this using the shorthand method, using summation notation. So what you first want to do is you want to look at the pattern, look to see what's changing and what's remaining constant, remaining the same. Okay, now if you see the portions that are changing is the 1, the 2, and then goes all the way to 8. So these are the values that we're going to be using as variables for using index to hold that value. And everything else that stays the same will remain those same values in our quantity. So we see that we can write this as the summation from 1 to 8, since that's the lower bound is 1 and the upper bound is 8. And we can simply write this as 5 times I over 8 plus 3. So we can double check our work, right? Plug in 1 in for I, and we're going to get the first term. Plug in 2 in for I, we're going to get the second term, and then so on and so forth until we reach our upper bound, which is 8. Okay. Number 11. Again, we want to represent the sum using summation notation. So again, we look at what's changing and what's staying the same. Okay. We see that what's changing is the numerator that's being multiplied to the 2. Okay. Notice that here we have, think of this as 2 times 1, and then 2 times 2, and then 2 times 3, all the way to 2 times n. So the portions that's changing will allow us to determine what is going to be our lower bound, what's going to be our upper bound, and also what's going to be our index variable, the portion that's going to hold the index variable. So the 2 over n, all this is going to stay the same. So I'm going to rewrite this as 2 over n cubed, 2 over n times, and then the outer term 2 over n. But the portions that's changing, we see from each of these terms, we're going to start with 2 times 1, 2 times 2, all the way to 2 times n. So then we're going to increment, we're going to put the value for the index as I next to the 2. So 2 times I, 2 times I. So we have 2 times I over n cubed minus 2I over n times 2 over n. Okay, we write this, or we can rewrite this as pull the 2 over n in front. Since we know that 2 over n is a coefficient. Okay, 17. Use properties of summation to evaluate the sum. So we have I in the problem, so we want to apply the appropriate summation formula rules. But first, we want to try and FOIL this out, to split this up into separate terms. So I minus 1 quantity squared can be FOILed out as I squared minus 2I plus 1. I'm going to split this up into individual summations. So the sum of I squared, the sum of I, and the sum of 1. And the 2 is a coefficient I can pull in front. Okay, so now replace I squared. We have a rule for the summation, sum of 1 to n for I squared, which is n times n plus 1 times 2n plus 1 all over 6. We have a rule for the summation of 1 to n for I, which is n times n plus 1 over 2, and then the summation of 1, which is just going to be n. Okay. Now we do have values. We do have values for our upper bound, so we can plug them in for n. So that's my next step. Plug in 20 in for n. Okay. Plug in 20 in for n here, and then plug in 20 for n here, and use your calculators. Simplify, and That's going to give us 2870 minus 420 plus 20, which gives us 2470. All right, let's see if I can do a couple more. Let's look at 31. Okay, find the limit of S of n as n approaches infinity. So this is going to be, think of this as finding horizontal asymptote. So we want to compare degrees between numerator and denominator, much like finding horizontal asymptotes. Okay, we're given S of n. I'm going to distribute everything through, and that will allow us to split them up into individual terms, and then we can evaluate the limit a lot easier, because then we can compare the degrees between the numerator and denominator. So FOIL the n plus 1 squared out to be n squared plus 2n plus 1. Distribute the n squared through, so I'm left with n squared plus 2n cubed plus n squared. Distribute the 81 through, distribute the n to the 4 through, and now when I compare the numerator and denominator, after all the brackets and parentheses have been dealt with, my numerator and denominator have the same degree, so I can simply find the horizontal asymptote by taking the values of the leading coefficients. So 81 divided by 4, so that's my limit. Okay. All right, let's look at 33. Okay. S of n is equal to 18 over n squared times n plus 1 over 2. Again, distribute through. And once I distribute everything through, I can see that, again, my degrees are going to be the same between numerator and denominator, both with a degree of 2. So simply look at the leading coefficient, 18 over 2, which is 9. Okay, if the degree is higher in the denominator, then that's where our limit will go to 0. If the degree is higher than the numerator, then we're going to go to either positive or negative infinity.